Imagine you're standing in a modern planetarium, surrounded by glowing screens and interactive displays showing real data from deep space. The night sky stretches endlessly above you, filled with countless stars and distant galaxies. But somewhere out there, hidden in the darkness, is one of the most extreme objects in the entire universe, a black hole. What would happen if you actually fell into one? Your journey begins now. Black holes are regions of space-time where gravity has become so incredibly intense that nothing, not even light itself, can escape once it crosses a certain boundary called the event horizon. They form when massive stars collapse at the end of their lives, compressing all their matter into an impossibly small point. The result is a gravitational field so powerful that it warps the very fabric of space and time around it. Let's say you're traveling through space in a spacecraft, completely unaware of the black hole's presence until it's too late. As you approach, you wouldn't notice anything unusual at first. From a distance, a black hole looks like any other massive object in space. But gravity's influence extends outward in all directions, and you'd feel it tugging at your spacecraft. Your instruments would alert you to the increasing gravitational pull, but by then, you're already committed to this cosmic journey. As you get closer, something extraordinary begins to happen. The gravitational field becomes so strong that it's different on different parts of your body. Your feet, being closer to the black hole, experience a much stronger gravitational pull than your head. This creates what scientists call spaghettification, or the noodle effect. The difference in gravitational force would start stretching you vertically, like taffy being pulled at both ends. It's one of the most extreme physical processes imaginable. The closer you get, the more intense this stretching becomes. Eventually, you'd be stretched so thin that you'd look like a long strand of spaghetti being pulled through the universe. This wouldn't happen all at once, though. Depending on the size of the black hole, you might be stretched gradually over several minutes, or the process could happen almost instantaneously. Size matters tremendously in the black hole universe. But before you reach the event horizon, something else happens. The accretion disk surrounding the black hole blazes with incomprehensible heat. Matter spiraling inward is compressed and heated to billions of degrees, releasing enormous amounts of radiation and energy. You'd be bombarded by intense X-rays and gamma rays. Your spacecraft would be irradiated far beyond any protection you could provide. The energy output from material falling into a black hole is staggering, making these some of the brightest objects in the entire cosmos. You're now approaching the point of no return, the event horizon. This is a spherical boundary around the black hole, and once you cross it, your fate is sealed. Nothing can travel faster than light, and light itself cannot escape beyond this point. From your perspective, time appears to slow down dramatically as you approach. Your instruments would show increasingly strange readings. Clocks would appear to tick slower and slower. To an outside observer watching you fall in, you'd appear to move more slowly, and your image would become increasingly redshifted, fading to darkness. As you cross the event horizon, you're committed to the black hole. There's no escape now. No amount of thrust from your engines could pull you back out. You're past the point of no return. But here's something remarkable. If you're falling into a large black hole, you wouldn't necessarily notice anything special at the moment of crossing. The event horizon isn't a solid surface you'd crash into. It's just a mathematical boundary, a point in space-time beyond which information cannot travel outward. Once inside the event horizon, your future is determined absolutely. You will eventually reach the singularity, the center of the black hole, where all the mass is concentrated. Physics as we understand it breaks down at the singularity. The equations of general relativity, which describe how gravity works, produce infinite densities and infinite curvatures of space-time. It's a place where our current understanding of the universe reaches its limits. The journey toward the singularity would be disorienting and horrifying. The intense tidal forces continue pulling you apart. The radiation and heat remain extreme. Space-time itself is so warped and twisted that concepts like direction and distance become almost meaningless. Time itself behaves strangely near the singularity. The normal flow of time, the distinction between past and future, becomes confused. What happens when you actually reach the singularity remains one of the great mysteries of physics. Your matter would be crushed to infinite density, or so the equations suggest. But scientists suspect that quantum effects, which we don't yet fully understand at such extreme scales, must play a role. Perhaps new physics emerges at the singularity, something we haven't discovered yet, that would prevent the truly infinite densities that classical physics predicts. Interestingly, the very nature of falling into a black hole challenges our understanding of information. According to quantum mechanics, information about the universe should never be truly destroyed. But black holes seem to violate this principle. Once matter falls past the event horizon, we can never recover information about what it was or what happened to it. This paradox, known as the black hole information paradox, remains unsolved by modern physics and represents a deep conflict between general relativity and quantum mechanics. The universe contains many black holes, and astronomers believe that supermassive black holes lurk at the centers of most galaxies, including our own Milky Way. These cosmic monsters can contain the mass of billions of stars, yet despite their power and mystery, black holes are also essential to understanding our universe. They reveal the extreme limits of physics and push us to develop new theories that might unite quantum mechanics with gravity. Falling into a black hole represents one of the ultimate journeys, a one-way trip to the edge of everything we understand. It's a sobering reminder of how vast, how extreme, and how mysterious our universe truly is. The black hole waits in the darkness, silent and patient, warping space-time around itself and pulling in anything that ventures too close. It's nature's ultimate boundary, a frontier that challenges everything we think we know about reality itself.